Now let's talk about how to actually solve spherical mirror problems. That is, you have an actual object that's closer to the mirror than some distant, infinite distance away from the mirror. So we have an object closer to the mirror. It's going to form an image. We want to know where the image is located and how big the image is. And that's what we're going to be talking about in this video. Now, we're going to use something called a ray diagram to actually determine where the image will be. So there are three key rays that we need to look at. Remember that objects have millions of light rays coming from them in all directions. But we're going to focus on three. The first is taking the object. So here's a mirror you have on the right. Center of curvature is here. Focal point is half of that distance, so it's right in between the mirror and the center of curvature. So you have an object out here. You take the tip and draw a line straight to the mirror. It's best to use a protractor or a ruler when you do these problems. Very important to get them as straight as we can. Anyway, a line straight to the mirror. Then once it hits the mirror, that light reflects and passes through the focal point F. We take a second point and we start at the object O prime here, have a light ray that passes through the focal point F, and then that reflects straight out. Notice how those two reflected rays now cross at one point. The third ray we want to look at is a line that goes straight from the center of curvature to the mirror and straight back. Since that's a radius line, that means this line is perpendicular or normal to the surface of the mirror. So any reflection comes along that same line, and sure enough, it meets at the same point. That point would be the location of your image. So if I had some object here in front of a mirror, I would see that object, but I would also see another image that my brain would say is located right here, slightly bigger than the original object and upside down. Great example of this, by the way, I should mention this is a concave mirror. And a good example of a concave mirror would be at the breakfast table. You pull out your spoon and you look directly into the spoon. Often you'll see your own image, your reflection, large and upside down. Now we're not talking about the back of the spoon. We're talking about the main part, the part of the spoon that dips downward. So you can actually experiment with a concave mirror using your breakfast spoon. So there are many other points we could have used to get a full image, but these three lines are enough for a concave mirror. Now, what if you want to do this mathematically? Well, we can do some geometry work, which your author has done. And basically what you have here is a set of, sorry, I want my pen. You have yourself two similar triangles. They're at the same angle, similar triangles, which means that ratios are, you've got some ratios that you can work with. And when you deal with those ratios, what you find is that if you take 1 divided by the object distance and add that to 1 divided by the image distance, oh, it's already labeled down here. That's all right. So if you take 1 divided by the object distance and add 1 over the image distance, that's going to equal 1 over the focal length. So I already have that down here. So those are the distances we're talking about. This is known for now as the mirror equation. We're going to give it another name in a few videos, but right now we're going to call it the mirror equation because this is what you're going to use whenever you need to find the object distance, the image distance, or the focal point of a mirror, given the other two. We can also find out how much bigger the image is going to be using the magnification equation, where m is the magnification. Simply, the magnification is just the ratio of what the image height is compared to its original object height. So it's just image height divided by object height. But using geometry, we find that that is also equal to the negative image distance divided by the object distance. Now, if your image height is negative, in other words, if your image height is less than 0, then your image is going to be upside down. That's what we mean by a negative image height. We have an upside down image. Also, I should also point out here that if you have a positive, sorry, not object distance, image distance. If you have a positive image distance, then you're going to have a real image. Again, remember earlier we talked about a virtual image, which is where light does not actually pass through the image. Well, here, light is passing through the image, so you have yourself a real image. And so that's a positive image distance. But there are some cases where your light will not converge at a point in front of the mirror. For example, if you have an object here inside of your focal point F. If you do that, you can do your 3 lines. There's 1 line. There's 2 lines through the focal point to the point coming back out. And the third through the center of curvature. These points will never meet up. So what you have to do is you take all of these reflected lines. Let me grab a highlighter. You take these reflected lines and you trace them backwards. So there's one reflected line. There's another reflected line. And last but not least, there's the last reflected line. You just trace them all straight back behind the mirror. As a result, you get all of your points crossing at this point. That's where your image is. Is the light really passing behind the mirror? No, it's not. Therefore, it is a virtual image. And since that direction is a positive image distance, then this direction is going to be a negative image distance. Notice also that your image is upright. So whether your image is upright, upside down, larger, smaller, real, virtual, it all depends on the location of the object and the location of the image. If you have an object that's outside of the center of curvature, let me come back here and say, in this case, we had an object between the focal point and the center of curvature, and we ended up with an image further out away from the mirror, inverted, larger, and real. With the object inside of the focal point, we ended up with an image that's upright, larger, and virtual. But now, what if you have an object that is, in this case, there's your object right there, the tip of your nose, that is outside of the center of curvature? Well, all these lines will cross right here at your image point. What you're going to see here is that you will have an inverted, smaller, real image. Okay, those are concave mirrors. Let's take a quick look at convex mirrors, and then we'll summarize everything up. Convex mirrors are weird. because light will never converge. If you have light coming in from the left, it will just bounce away like so. There's no way that this light will ever converge. So what do? We do exactly what we did earlier. We take our light rays and we trace them backwards. And when you trace the reflected rays backwards, they all cross at one point. You got it, that's the focal point. Now, since the focal point is actually behind the mirror, then we actually say that the focal point is going to be negative. So for a convex mirror, the focal point is negative. But for a concave mirror, which is what we dealt with in the last few slides, the focal point is going to be positive. And what you're always going to see with a convex mirror, no matter where the object is, you're always going to see an upright, virtual, smaller image that's going to be somewhere between the mirror itself and the focal point. That's always where your image is going to be for a convex mirror. And when you do your lab on this, you'll be able to play around with this and you'll see that for a fact. So how do we solve problems with spherical mirrors? The first step is to draw a ray diagram. This gives you a good general idea of where the image is and whether the image will be upright or upside down, real or virtual, larger or smaller. So it gives you a good beginning step. The second step is to apply the mirror and the magnification equations. Doing this week's lab, you will be able to see all of this in action. You'll be able to see how all of these equations work. And then you have to remember your sign conventions. Remember that if the object and the image and the focal point are on the reflective side of the mirror, then their values are positive. But if the object, the image, or the focal point are on the back side of a mirror, then you're going to have a negative distance value. And magnification will be positive if the image is upright, but magnification will be negative if it's otherwise. And then last but not least, check to see if your math from steps 2 and 3 agree with your diagram from step 1.